problem sets 10.1 and 10.2. Let me get a marker so that you can see it a little bit better. 10.1 and 10.2. I'll write that on my paper and I'll show it to you in a second. I'm going to do 10.1, 10.2 problem sets. And those problem sets are on pages 307 to 322. And your learning program wants you to do numbers 1 to 23. Okay, I don't want to do all of them with you, obviously, but we are going to do enough of them so that you can know how to solve the problems yourself. Okay, so let's go to the camera. And there is the camera. Here's my paper. I wrote problem sets 10.1, 10.2, chapter 10, section 1, chapter 2, 10, section 2, pages 307 to 322, and then numbers 1 to 23. Okay, so let's get started with that. Now, let's see, I am going to need to be able to see this. And hopefully I can find some glasses around here. Let's see, open my drawer. Gosh, happened yesterday too. Okay, so here are my glasses. Let's go to page 307 and let's see what they want us to do. Okay, so page 307, here we go. The problems are actually, on this part right here tells you how to do the problems. And then there's some problems down there, and then there's some problems at the end of the section. So this one right here, as you can see on the screen, says sample problem 10.1. What you're doing is finding mass from a count. What is a mass of 90 average size apples if 1 dozen of the apples has a mass of 2.0 kilograms? So what you got to do is use dimensional analysis, which we learned back in September, to try to figure out stuff. So what you need to do is write down what you know. And what do you know? You know there's 90 apples. You start with what you know. And if you have 90 apples, and this is example 10.1. And I'll write the page number on page 307. Okay, so you have 90 apples, and it tells you that you have a dozen of the apples has a mass of 2.0 kilograms. Well, what's a dozen? A dozen is 12 apples. So when we use dimensional analysis, remember the next unit has to have its unit on the bottom of the conversion, the conversion factor. So the conversion factor is, we know that there are 12 apples in 1 dozen. And we know that, and from what they told us, is that each dozen weighs 2 kilograms. So I'm going to put dozen over there so I can cancel it. Top, bottom, top, bottom. And the masses of 1 dozen, it's 2.0 kilograms, which is what I wanted. So what is the mass of 90 average size apples? So I start with 90 apples. Here's a conversion factor. The top is the same as the bottom. 1 dozen is 12 apples. 1 dozen weighs 2 kilograms. And so when I do that, okay, so let's go to the phone, get my calculator out, and I have 90 apples times 1 times 2.0 equals, so that's my numerator, Divide by 12 times 1, it's just 12. So that is 15. So my answer is 15. That's my numerical answer. But if you look at what I canceled, you can cancel out apples, top and bottom. You can cancel out dozen, dozen, and you're left with kg. And that's exactly what we wanted, 15 kilograms. Box your answer, show your work. Yay. Okay, so that's how you do that. Well, let's try one of the assigned ones. And it says down here, you can see it, it says, if 0.2 bushels is 1 dozen apples and a dozen apples has a mass of 2 kilograms, what's the mass of 0.5 bushels of apples? So we're going to start with what they give us. They said, what's the mass of 0.5 bushels of apples? So I'm going to start with 0.5 bushels of apples. Okay. Now remember the 0 there is not significant. So it's really the answer should be just to one significant figure. Okay, so I have a bushel up here, but as I look at my conversion factors, is there a conversion factor with bushel on the bottom? Because I'm going to need bushel on the bottom so I can cancel that bushel. Well, they say if 0.2 bushels, 1 dozen apples, and a dozen apples has a mass of 2.0, but the mass of 0.5 bushels of apples. Well, there it is. If 0.2 bushels is 1 dozen, then that's my first conversion factor. So 1 dozen is 0.2 bushels. Well, I wasn't trying to get dozen. The question is, what is the mass of 0.5 bushels? So I have 0.5 bushels. I have 0.2 bushels equal to 1 dozen. The only other info that I have is a dozen apples has a mass of 2.0 kilograms. So a dozen apples, and this is going on the bottom so I can cancel the top. A dozen apples has a mass of 2.0 kilograms. And the question is, what is the mass of 0.5 bushels of apples? So if I do my math again, this is what I get. I get 0.5 bushels times 1. You can put that in your calculator if you need to. And then here's 2.0. 0.5 times 2.0, you can do that one in your head. That's 1, right? And then 1 divided by 0.2 equals 5 altogether. So the numerical part of my answer is 5. And the units are, if we cancel like we did in the previous one, bushels cancel, dozens cancel, and I got 2.0 kilograms is what I have left. So the answer to number 1 right there, the answer to number 1 then is 5 kilograms. Now, do I have the correct number of significant figures? I had 2 there. I only have 1 here and here, so 5 kilograms is correct. I don't have to put 5.0, but just 5 kilograms as my answer. Box your answer, show your work. All right, so that's how you do the first sample problem in 10.1. And this is on page 307, you guys. 10.1, and over here, we just did this one together. Okay, and then that is the answer is 5 to that one. Hopefully you can do number 2 on your own. Let's go and do a different type of problem. Here's 10.2. 10.2 is converting number of atoms to moles. Number of atoms to moles. Okay, well, what you need to know is this number down here. This is called Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. That means from this decimal to the right, there are 23 spaces. That means it's a 6, 0, 2, and 21 zeros after that. Okay. Now that equals 1 mole of any substance, but then you can also flip-flop this just like they did here, because it's a conversion factor. Okay, this is the other way to write a conversion factor. Remember, we went over all this back in September. If you need to, you can go back and look at my lecture on dimensional analysis. Okay, so what's the question? The question is, magnesium is a light metal used in the manufacture of aircraft, automobile wheels, and tools. Okay, that's all nice, gives you background information. But as far as solving our problem, for example, 10.2, that doesn't help us much, that information. It doesn't help us at all. What we need to know is what's coming up. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? So you start with what they give you, which is 1.25 times 10 to the 23rd atoms. And you're going to take that number and use the conversion factor. The conversion factor is that in 1 mole, there's going to be a certain number of particles, and that's called Avogadro's number. I'll write that over here. Sometimes we say N sub A for Avogadro's number. And Avogadro's number tells us that 1 mole of any substance is made up, I shouldn't put a equal, but it's more like a definition. 1 mole of any substance is equal to 6.02 times 10 to the 23rd parts. Could be particles, could be atoms, could be molecules. Just like 1 dozen is made up of 12 pairs, 12 eggs. You can say a pair equals the 2. You can say a ream of paper, 1 ream of paper equals 500 pieces of paper. Similarly, 1 mole is equal to this number. Now it's an unusually big number, but still just the same way, right? So 1 mole is equal to 6.02 times 10 to the 23rd parts. So back to our problem, if we have this many atoms and we have this conversion factor, and we're trying to get to how many moles, well, then what we're going to do is we're going to take that and instead of parts, this could be parts or particles, or it could be atoms, or it could be, you know, just about anything. In this case, we want the atoms. So we're going to say, so that we can cancel that out, I'm going to put this part on the bottom and this part on the top. So 6.02 times 10 to the 23rd atoms of magnesium equals 1 mole of magnesium. A mole spelled M-O-L-E, but we abbreviate it M-O-L. I know we just dropped the E, but that's what we do. Okay, so now here's what you get. You could do this on your scientific calculator. If you have an iPhone like I do, what you can do is turn that, and you can say 1.25, 1.25, this number right here, 1.25 times 10 to the 23rd is that EE button right there, times 10 to the 23rd. We're going to take that number and divide it by 6.02 times 10, EE times 10 to the 23rd equals that, and that's your answer. Your answer is going to be, and there's 3 sig fig, so I'm going to say 0.208, 0.208 moles of magnesium. I'll box my answer. Just showed my work right there. Okay. Now with the calculator, you can also do it this way. Remember that if you have fractions, well, if you if you have scientific notation and it's in a fraction like this, then what you would do is divide the mantises and then subtract the exponents of the powers of the base 10. So this is going to be 23 times 23, which is 0. So if I'm, just to show you what I'm doing, I could say 23 minus 23 is 0. And then with the calculator, it's 1.25 divided by 6.02 equals, and then there's my answer, 0.208 times 10 to the 0 power. 10 to the 0 power is 1. 1 times any number is that number. And so your answer again is 0.208 moles of magnesium. So there it is again. Box your answer, show your work. Okay, so now that you have that 10.2 right there, let's go ahead and go raise that up so we can see more of the page right there. Let's do one from 10.2. It says down here, how many moles is 2.80 of 10 to the 24th atoms of silicon? They give you this, the number of atoms, and use this factor again to get your answer. Same here. Oh, this time it's how many moles is 2.17 times 10 to the 23rd representative particles of bromine? Well, it says particles, so remember parts, particles, atoms, whatever the unit is. Well, we're going to take this guy right here, 2.17 times 10 to the 23rd, and divide it by 6.02 times 10 to the 23rd, Avogadro's number, n sub a, right there. Okay, and so number 4 is going to be just like our example. They want us to get moles, and we did get moles. Same with number 3. They say you have this many atoms. How many moles do you have? So that 6.02 times 10 to the 23rd number is the same whether you have magnesium or silicon or bromine. Okay, and so we're talking about parts or atoms or particles, anything like that. Okay, so you don't even need to do another one of those. Let's go to 10.3. 10.3 says converting moles to number of atoms. Well, to do moles and number of atoms, you start with what they give you. And so this is 2.12 moles. And they want to know how many atoms are in 2.12 moles. So here's what we're going to do. We're going to go and take a look at, let's see. This is sample problem 10.3. And so we're doing the right 10.3, and this is on page 311. Okay, so here's what they give us. They say propane is a gas used for cooking and heating. How many atoms are in 2.12 moles of propane? And they tell you propane is C3H8. So here's what you know, and you can do it this way before you even set up the problem. I kind of skipped a step on the first couple of examples there, but you can write it out and you could say, all right, so here's what you have. You have the number of moles, and you know that there are 2.12 moles of propane. Okay. Now here's another thing you know. You know that if you look at it, you look at the subscript right here, look at the subscripts, you can see in one propane molecule, there's 3 carbons and there's 8 hydrogens. So there's 11, 8 plus 3, 11 atoms altogether. Because that's what our question was hinting at. How many atoms are there in that many moles? Okay, so I have that many moles. Okay, that's what I'm starting with. And there it is again. I have 2.12 moles of propane. Okay, and I also know that in 1 mole, you have 6.02 times 10 to the 23rd atoms, you could say. Okay. And so what we'll do is we'll figure out how many particles you have, but then you got to understand and I'll write moles of propane. Okay. In 1 mole of propane, you're going to have, let's see, I'll say 1 mole of propane, you're going to have 6.02 times 10 to the 23rd molecules of propane. But for propane, for each molecule that you have, we counted it out. For each molecule, you have 11 atoms, which is what we wanted. That's what the question was. The question was, where to go? How many atoms are there? So moles are going to cancel. Molecules are going to cancel. Atoms are what's left. So let me go back to the calculator and put in 2.12 moles of propane times 6.02 times 10 to the 23rd, and then multiply that times 11. And so there's my answer. My answer is, and I have 3, 3, 2. So I've got 2 significant figures. Let's see. So that's the example. And in the example, I've got 2 significant figures. And where are we? Well, actually, this is a counting number. You know, to remember when we counted, those don't count towards uncertainty. And those are exact numbers because you counted exactly 11 atoms in a molecule. So that doesn't count for sig fig. We have 3 there. We have 3 there. So our number needs to be in, our answer needs to be in 3 significant figures. So it's 1.4. And drop the rest to the 10 to the 25th, e to the 25th power. So 1.4 times 10 to the 25th atoms is how many atoms we have in 2.12 moles of propane. In the box, my answer. And that is how we do number 3. And let's go. Oops, I said it, but I didn't write it right. 1.40. 1.40 times 10 to the 25th atoms. Okay. All right. So that's how you do that, guy. Let's go to 10.4, and I'll do those sample problems with you so that you can see it done. And you can hopefully use that experience to answer the questions underneath here and also over here. So this next one is the sample problem on page 315 for 10.4. Righty. And you have, what you're going to do is you're going to find the molar mass of a compound. Okay, it's like the atomic weight of an atom. Well, now it's a molar mass of a compound. So what was the problem here? The problem is, okay, the decomposition of hydrogen peroxide, which is H2O2, provides sufficient energy. So sufficient energy to launch a rocket. What's a molar mass of hydrogen peroxide? Well, here's H2O2. And you can see that H2O2 is one molecule that is made up of two hydrogens and two oxygens. Well, let's do the hydrogen first. The hydrogens, we know there are two of them. And well, how much is a hydrogen weigh? Well, I know my head, it's 1.008. How do I know that? I go back to the periodic table of elements on page 168 and 169. And you can see right here, hydrogen 1.0079. So the one I have in my head is 1.008. So that's what I use. And there you go. So what you're going to do is multiply that together. You're going to get 2.016. Alrighty, and for the oxygen, you can see there are also two of those. And if you look back at your periodic table, the atomic mass of an atom of oxygen is 16 or 15.999. And so where's that? There it is right there, 15.999. I'll go ahead and write that in. 15.999, and that's going to be very close to 32. It's going to be 31 point, what is it, times 2, 31.998. So I'm going to add those together, 31.998 plus 2.016. Oh, you can't see. Why didn't you say something? All right. Plus 2.016 is equal to 34.014. 34.014. Nothing that tells us anything about significant figures. I have 4 right here, 5 right there. So I'm going to go to 4. So this is going to be 34.01 grams for every mole of this stuff that you have. It's going to weigh 34.01 grams. And so that's called the molar mass. That's a molar mass of H2O2. Okay. So again, you got to take each element, figure out how many you have with the subscript, and then multiply it by the atomic mass that's found on the periodic table of elements. So that is how you do 10.4. Okay, let's go and try in section 2. There are different types of problems there. These are a little more difficult, but they're just a different type of problem. Okay, so let's go to 10.5. Here's 10.5. 10.5 says converting moles to mass. Moles to mass. All right, so here's the question. It says items made out of aluminum, such as aircraft parts and cookware, are resistant to corrosion because the aluminum reacts with oxygen in the air to form a coating of aluminum oxide. That's important. Al2O3. This tough resistant coating prevents any further corrosion. What is the mass in grams of 9.4 moles of aluminum oxide? What is the mass in grams of 9.4 moles of aluminum oxide? Well, what we got to do first is we got to figure out how much 1 mole of aluminum oxide weighs. And then we're going to take that 1 mole and multiply it times 9.45. Well, how do we figure out how much 1 mole weighs? Well, it's a molar mass, and we just did that. So this will be a good way to review what we just did. We have Al2O3. We have 2 different types of elements, Al and O. We have 2 Als, and we have 3 Os. You know, 3 is, O is 15.999. Do you know aluminum right off the top of your head? I actually don't. So I'm going to go back and I'm going to go to 169 and I'm going to find aluminum right there. And aluminum is 26.982. I'm going to write that down, 26.982. We're going to multiply that out. Hey, Siri. Oh, I don't have the Bluetooth on. Okay, so hang on a second. We're at 26.982 times 2 equals 53.964. And I got something close to 48. All right, so I'm going to go 15.999. Oops. 15.999 times 3 equals 47.997. I'm going to take that 47.997 and add to it the 53.964. And my answer is 101.961. I think we can do it to 5 sig fig. So 101.96 is our molar mass. But I know that there's not just 1 mole. From the problem, it says I have 9.45 moles. 9.45 moles. And I just figured out that this is that the molar mass is 101.961 grams per mole. So mole is going to be on the bottom. That's 1 mole. 1 mole weighs 101.961 grams. And the question is, what is the mass in grams of this many moles? So I'm going to take that 101.961. And remember, you want to round off at the end times 9.45 equals 963.5314. Well, I'm going to have 3 significant figures. So 963.5. And so this is 0.5. And since it's 0.5, I'm going to round it up. And this is going to be 964 grams. You can say 964 grams of aluminum oxide, and that would be your answer, 964 grams. And so that's how you do sample problem 10.5. Let's go ahead and do, let's do all of them, right? Here's 10.6. 10.6 says converting mass to moles. 10.6. When iron is exposed to air, it corrodes to form red-brown rust. Rust is iron 3 oxide. Okay. Remember, we learned about this when learning how to name. This means that this has a 3+ charge. And because it has a 3+ charge, this will come into play when we figure out the formula for the compound. And it's Fe2O3, and they give it to you right there. And so the question is, how many moles of this do you have? If you start with, if you have 92.2 grams of Fe2O3. If that is the mass, then how many moles is that? Okay, so what we have is 92 grams of Fe2O3. We want to know how many moles there are. Okay, but what we need to know is, well, we need to know the molar mass of just Fe2O3. So we've got to figure that out again. There's Fe2O3. So we have 2 ions and we have 3 oxygens. So iron going to the periodic table, which again is on page 160, 160 something. I have a post-it in it. Some books will put this at the very end of the book because you use it so often. Okay, so we're looking for iron. There it is, 55.847. And then oxygen, we have 3 of them, and each of them weigh 15.999. We're going to add those up again. So multiply them, and then we're going to add those up. So that's calculator. We have 55.847, and that is going to be times 2. Okay, so that's 111.694, and then 15.999 we saw previously was 47.997, or you could do that one in your head, but add that right here, 47.997, and that equals 159.691 grams. So that is the molar mass of iron oxide. And what was the question? The question is, when iron is exposed. Okay, so here's the question. How many moles of iron 3 oxide are contained in 92.2 grams of iron oxide? So that's what they've given you, 92.2. So we're going to start with that, 92.2 grams of iron oxide. Well, I'll go ahead and put iron oxide there. That's how many grams we have now. When we go to dimensional analysis, our next conversion factor has to have grams at the bottom. Well, guess what? We know that already. We know that 159.691, we just figured that out. 691 grams for every mole of Fe2O3. Guess what? That's what they wanted us to find out. How many moles is that? So all you gotta do is multiply that out. And so what you're gonna get is a very simple calculator. If I had a reciprocal, I could have just pushed that. 92.2 divided by 159.691. Here's what the calculator gives us. And we have 3 significant figures right there, 92.2. So we're just going to say 0.577. And so that is the answer. The answer is 0.577 moles of Fe2O3. And that's how you do that one. That's 10.6. Okay. And then we'll go to try 10.7 and 10.8. Okay, so it's 10.6. Let's do 10.7. 10.7 looks like this. It says calculating gas quantities at STP. Sulfur dioxide is a gas produced by burning coal. Okay, that's nice. Gives you background. But for the solving of the problem, what do we need to do? All right, so it's an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.6 moles of SO2, that's sulfur dioxide, gas at STP. Now, we haven't done STP yet, but STP means standard temperature and pressure. Okay? Because you know, the volumes will change with changes in temperature and pressure. So we need to state what the temperature and pressure is. So when we say in a problem, STP, standard temperature and pressure, we know this is at 0 degrees Celsius. And we know this is the pressure of 1 atmosphere, which is what it is at sea level. An atmosphere is also known as 760 millimeters of mercury is another way to say that. And instead of saying millimeters of mercury, sometimes we say it's a torr. And so those are other ways to measure pressure. Okay. All right. So this is just saying that we're measuring it at a standardized temperature and pressure, so we can make all of the we can use those numbers because those numbers won't be changing. Another thing you need to know is that the volume of a gas at STP, volume of a gas at STP is always equal to 22 liters. Okay, so that's something we haven't come across yet. It's actually, we usually say 22.4 liters. So that's another number you're going to need for this problem, okay, 22.4. So let's look at the problem now that you know some background info. Determine the volume in liters of 0.6 moles. All right, so you've got 0.6 moles of this gas, and the gas is sulfur dioxide. Well, and you know you're at STP. Well, then you know that 1 mole of any gas at STP has a volume, oh, you can't see. I have 0.6 moles given. Well, what I was saying over here is that 1 mole has a volume of 22.4 liters. And that's what we wanted, and these are going to cancel out. So all you have to do here is say, okay, 22.4 times 0.6 equals 13.44. So the answer is 13.44 liters for number 7. Okay, and let's see. They actually gave us 2 sig fig here. So our answer really should be the 2 significant figures. So let's make that then just 13 liters of SO2 as our final answer. So 13 liters of SO2. Taking that answer and pulling it to 2 significant figures. So that's 10.7. Go one more. We'll try 10.8. Okay, 10.8, you have calculating the molar mass of a gas at STP. Density of a gas's compound containing carbon and oxygen is found to be the density. Sometimes we simply say D, but the better abbreviation for D is that right there. Okay, and so this density is equal to, and that's the Greek letter rho, by the way, RHO. Density is equal to mass over volume. And in this case, what they're telling us is that the density of a gas in this formula, I mean, in this problem is 1.964 grams for every liter. Okay. Do the whole thing. What is the molar mass of the compound? The molar mass, remember, is how much a mole weighs. So we want our answer to be in grams per mole. Now we know the density. The density is 1.964 grams for every liter. Well, we need a conversion factor to get rid of grams. Okay. And what we want is, it says a molar mass. Remember, molar mass is going to be grams over moles right here. Well, the conversion factor we know is that for every mole of a gas, 22.4 liters. So I want the grams to be on top, but I want moles to be on the bottom. So if I put this L on the top and I put moles on the bottom, and that's what I got, grams over moles. Grams over moles, the two L's cancel out. Well, what's the number? The number is 22.4. By definition, there are 22.4 liters. That's the volume. The volume of any gas at STP is 22.4. So I'm going to clear this out. I'm going to go 1.964. And since these are both on the top, I'm going to multiply them together times 22.4. Oops, that's not right. 22.4 times 1.964. And what I did was, I saw there was a negative, so that's not going to be right. And I can also eyeball it and say, that's about 2, and this is about 20. So 20 times 2 is 40. My answer should be a little over 40, 43.9. So L's cancel. My answer makes sense. It is 43.9936. And I have 4 significant numbers right there, 4 sig fig. So my answer is going to be 43.99 grams per mole. Box that answer. Work is shown here. Ooh. So you have the sample problems worked out for you, but we just did them together, and hopefully now that you've seen how to do it, then you can actually do the problems yourself. You're supposed to do 1 to 23. And the reason I did all 8 of the sample problems, because most of them have a sample problem and then 2 problems. That's 10.8. Here's a 10.7. There's the sample problem and then 2 problems. Let's go 10.6. There's the sample problem and 2 problems. So I've given you all these sample problems, and we've seen how to do it live. Hopefully you can take that information and you can go and solve all those problems, okay? All right, let's stop the screen share. Ask if you have any questions.